I'm here again today with Glen, and according to the comments in our last episode together, he's the favorite guest on the channel. So I hope you all are looking forward to his talk today. We are going to, I guess, tie up the loose ends on the Jordan Peterson-Lawrence Krauss conversation and hopefully end up with talking about free choice and entropy and how they either do or do not connect. And I'm going to let Glen get us started. I've been studying like mad for this, including reading Cesar Hidalgo's book on how information grows. And also I went back through all 6 episodes of our What is Life series that you and I did together. And I printed out the show notes of all 6 episodes and I went over them, and there's a lot of amazing information in there. So I've been having fun studying for this, and I look forward to our conversation.
Wow. Okay. And I noticed the comments, and I'm really happy. I hope your viewers realize that I think it took you about a year to finally talk me into showing up and opening up on this channel. So you're the hero in all this. So
no, I'm the recipient of all this generosity is what I am.
But as I was getting ready to tie up the loose ends of the Lawrence Krauss Jordan Peterson talk, we were getting into the notion of what a free choice was in physics. And I know you've been curious about that, and I've looked at a lot of our conversations on email over a year now, I guess.
No, I think we've been conversing by email for over 3 years now, actually.
Oh,
it goes back a long ways.
I'm that old. Anyway, and I know entropy has always been a big question for you. You always keep coming back to that. And I always keep wanting to give you a good answer, because the questions, you take things beyond the textbook answer. And so here we go. And as I thought about what I was going to say for this talk, the more I realized that we have actually come full circle to my first conversation about the origins of life. Because the origins of life is just kind of a sub-question underneath why complexity grows in this universe. Jordan Peterson and Lawrence Krauss touched on that sort of tangentially during their talk about, is order, disorder, is that where the universe is going? But there always seems to be this tendency for complexity to grow out of disorder. And so that's what we're going to deal with today. We're going to start looking at that question. Now, the term consensus science has kind of gotten a bad rap lately. But it does have a place. It is a useful concept. And essentially, it's just what you learn textbook-wise when you're an undergraduate. It's what you hear when you go on YouTube and you listen to some of the popular science lectures. It's a generally accepted body of knowledge that everyone kind of agrees on that, okay, we know that much. But if you're going to do research in any field, physics for me, the very nature of research is to question the consensus opinion. That's where research happens, at the frontier, where you're actually asking questions, seeing what's wrong. And when you study a course in school, you learn the textbook approach. You learn the answers, but they don't teach you how to ask questions. And that's something you kind of have to learn on your own or by trial and error when you're a grad student. Is you're out there on your own now. There's no textbook you can look up, no professor you can go ask. So you need to learn the skills, develop your intuition. How do you know when you're right? How do you sense when you're going in the right direction or not? How do you keep going when everybody's telling you you're wrong? So that's a skill set in itself, I think, that a lot of people don't learn. But it's very useful. And I've kind of been impressed or amazed with your viewing audience, is I think the people that visit your site are up for that. that it's a selected group of people who are ready to jump in and take the risk and go out there and see what happens. So that's what I really want to talk about today. I don't have answers. I'm not going to give you my theory of everything. I have thoughts, opinions that have come about because of the way I approach physics, the questions I ask, what I look for. And that's what I want to share today is the process that I go through when I approach these questions. And hopefully that will be more helpful than just giving an answer. So we'll start with the idea of consensus. And we're going to push the envelope. We're going to go walking out into the frontier. And when you're out there, you have to start asking questions. And you look for the answers that you don't get. And that's the anomaly. I know you always like that. So I've decided that anomaly plus curiosity is how you advance in science. And along the way, when I was thinking about this, it took me back to a wonderful quote from Friedrich Nietzsche.
Mm-hmm.
In his book, The Twilight of the Idols. Talks about sounding out idols. And I'll read it in English. It said, another way to recover, which under certain circumstances I like even better, is sounding out idols. There are more idols than realities in the world. That's my evil eye on this world and my evil ear too. To pose questions here with a hammer for once, and maybe to hear and reply that well-known hollow tone, which tells of bloated innards. How delightful for one who has ears even behind his ears. For me, the old psychologist and Pied Piper, in whose presence precisely what would like to stay quiet has to speak up. So what he's saying is that you probe the truth by asking questions. And in the German, this is one of the few times in my life I actually made the effort to actually read an author in the original German. And so I tried that back in my youth when I had plenty of spare time and craziness. I tried to read excerpts from Nietzsche in the original German, and it was quite an eye-opener because I found out that the original German often is different than the English translation.
Mm. Oh yeah.
He was a master wordsmith. He was a master of the one-liner. He used a lot of double meanings in his words, which you miss if you read in translation. And he can be very sarcastic, which doesn't come through. So I've decided that he is the Don Rickles of Western philosophers. So I think we just dated ourselves by making that comparison. So so you have to take some of his stuff. There's a bit of humor in there, which doesn't always come through. But anyway, in German, about the hammer, he says, hier einmal mit dem Hammer Fragen stellen und vielleicht als Antwort jenen berühmte hohlen Ton hören. Sorry for my German. But this is a wonderful image because in German, you don't ask a question, you stand it. And to me in English, to ask a question is sort of a passive thing. But the German reflection is you stand a question, you put it out there, put it before the idol, and it stands before you, And it gives this impression that a question is a thing in itself. It's a standalone complex, to borrow from Ghost in the Shell. It doesn't need outside support to stay up. And I've noticed with a logically framed argument is capable of standing by itself. It doesn't need support. It doesn't need enablers. But arguments based on emotional appeals, they require that constant reinflation of emotions to keep them up. So that's always a thing I look for is can your argument stand by itself? Can you put your ideas on paper and walk away, and that they'll carry their own weight?
Now, that's one thing they talk about in art too, is that You shouldn't have to put a card next to your painting explaining what it means.
Mhm.
It should be saying something to the viewer without you explaining to them what your intention was.
Yeah, that's the general rule in life. If someone has to keep reminding you that they are X, then
Yes.
they're not X.
Yeah.
But I want to get back to the analogy, because when this is like 40 years ago, I was reading Nietzsche, actually more than that. But I read that posing questions with a hammer. And I read some of the commentaries, a handful that I read. They presented it as if he was going around hitting things. But it's not. There's a wonderful image there. And I thank goodness that I was a physics major, because I saw it. This is a reference to.
Oh, looks like I lost Glenn. I'm going to put it on pause here. You're back. Cool. We lost you for a second.
Yes, well, it went out and it came back. So should I start over, or should I just keep going?
Well, let me just recap what you said. You were talking about Nietzsche, that his idea of posing questions was the hammer, and people thought that he was going around hitting things with his questions, but that's not what it was at all. And you're thankful that you were a student of physics, because it enabled you to see what it was he was getting at.
Yes.
Okay.
So here's where this lost connection. It's a reference to bell making. Imagine if you grew up in the mid-19th century, bells, whether the church bell or the tower bell, the center of the city, would have been a common experience. But that bells have sort of gone out of our collective consciousness. So the analogy that he's trying to paint, I think, we miss it. When you're manufacturing a bell, it's quite a process. From the pattern to the mold to melting the metal, getting the alloys right. If you let the bell cool after it's been cast too fast, it will crack. So you have to let everything sit. Sometimes for a large casting, it might be weeks to let it cool down slowly. Now the bell's ready, you break the mold, you take it out, you clean things up, you scrape off the edges and stuff. So if there's hidden flaws in the casting, when the casting first comes out, the skin is going to be nice and smooth. You won't see any hidden flaws. There'll be stress points that haven't cracked yet, but if you put the bell outside, the heat and cold of winter, summer, the banging, those little tiny, inconsistencies will grow and turn into a crack, and the bell will break. So how do you find out where those hidden flaws are? And the answer is you strike it with a hammer. You start hitting it and you'll get the ding, ding, ding. But if you keep going around until you find ding, ding, dunk. And what's happening is when you hit it with a hammer, you set up vibrations, different modes. And if the flaw sits at a node in the vibration mode, you won't hear it. The bell will ring true. So you have to excite a vibration where the antinode falls at the flaw, and then you'll get the thunk sound. So I love that image, because even a flawed bell will ring true. I wonder if that's where the expression comes from. If you only hit it in the right places. To find the flaw, you have to hit it all around in different ways. And so when he's talking about sounding out idols, he's saying you ask questions and you listen for the answers. And you don't just ask a few questions, because even an idol can give you the correct, true answers some of the time. So you wait until you find the answer that it can't give, or it won't found the flaw. And I think this is great advice in life in general. If someone's trying to make an argument and you start asking questions, And then you find that one question they will not let you ask, or they won't answer, that they will whack you back if you try and ask it. Lesson, idols can still give you true answers if you only ask the right questions. You have to ask all of the questions. So
Well, I mean, that totally makes so much sense when I think about how Jordan Peterson talks about ideologies being incomplete religions. They try to package everything up, but there's parts missing, and because those are missing parts, there's questions that can't be answered, and that's exactly what makes it an ideology.
Right.
Yeah.
I wonder if idol and ideology have any.
Yes. Oh yeah,
connection.
absolutely, completely, because they act exactly the same way. They narrow your frame of reference down, and it causes an internal narrowing of your perspective. A continual reciprocal narrowing is the way John Vervaeke puts it, right? Addiction does that, ideologies do that, idols do that.
So I was thinking, well, we'll just take it a little more dispassionate view. We'll take that out of our day-to-day life realm and pull it back to the science. That same asking questions applies. You know, when you're out beyond the textbooks, you're out in the frontiers. How do you explore? How do you go? You ask questions, and you keep asking questions until you find the question that the physics, the current understanding, the consensus can't answer, that missing piece. And you can't be intimidated. You can't be afraid to ask stupid questions, because in that realm, there is no stupid questions. And people, don't feel dumb, The consensus view says that something should work a certain way, and then you look, and then there's nothing there. I imagine sometimes going into a theory is like walking into this room, and it's supposed to go into the next hallway, and there's a wall there. And you go, okay, we're missing something. Now let me take a break here.
Well, sure. Well, while you're taking a break, I'm just going to say, one of the reasons I keep asking questions about entropy is that I think entropy is one of those things that is used differently by every single arena of science, and all the different systems use it in such a different way, and you use it in a different way than they do, and so it's really difficult to find where the questions end.
I'm afraid we lost our connection again.
Oh, did you lose me? I lost you for a minute, but I'm going to put it on pause for a second. So Glenn, you were saying?
Okay, we'll try again. So that's the approach I'm going to start taking now. We'll start asking questions. And this is where I think Jordan Peterson, Lawrence Krauss completion takes us back to the beginning. If we start looking at why complexity grows, that's the question, why? And if you look at all of the theories out there and the different, approaches, there's no answer. No one can give you a good answer. So generally what happens in physics, you don't go there because there's no publications and no grants. So it dead ends. But we will keep going. So why complexity grows? Before you can ask the why, there has to be a how. And I noticed that's one thing always missing in these discussions. Again, like I say, I asked the question why, and then I realized, well, there's no way to answer why until I answered how. So now I go exploring for how. What is the mechanism that lets complexity grow in the first place? When you would think everything wants to become random, you just go to a general state of disorder. But then I ask myself, well, what do we mean by disorder? When we use that term in thermodynamics, we're referring to the final equilibrium state of a system. You know, that using entropy as a measure of disorder only works mathematically if you're talking about the final equilibrium state. It doesn't tell you how the system got there in the first place. So again, I ask that question. I'm not happy, I'm not satisfied with the answer that entropy is a measure of disorder because it's not telling me how I got there in the first place. It doesn't give me a hint or a clue or a mechanism to explain that. So then I step back, okay, what is happening at each step of process? Non-equilibrium thermodynamics, that's a big area. And I think we might have touched on it here and there with some of the authors that have come up. So it's better to think of entropy not as a final state, because in the universe, that's very seldom, if ever, the case. A process. Ask the question, what is happening at the step-by-step, whatever scenario that gets you to the final disordered state? So then you come back. How does anything happen? How does causality happen? And you've brought up the question of constructor theory, and into that, and we can have a talk some other day. I would consider it a rather incomplete attempt or restatement of strong emergence. But a lot of people in physics don't like strong emergence. In fact, there seems to be a correlation in my experience between people who reject strong emergence and people who are vocal atheists. I don't know what the connection is. That might be an interesting discussion. But David Deutsch in his paper, I'll quote, "Causation is widely regarded by philosophers as being at best a useful fiction, having no science." Hume, 1739, argued that we cannot observe causation and therefore can never have evidence of its existence. So we talk about things, causation, something happens, causes something else to happen. What David Deutsch is pointing to, and Hume, is where does that moment happen? And now I think we're getting back to the question of free choice. And we had that great video that came up in the last talk on do electrons have free will?
Mm-hmm. You want me to bring that up and show starting at 43?
Yeah, 43.
Okay. I'm going to start it a little bit ahead because sometimes my sound is kind of wiggy, so hopefully it'll do the right thing. More than a little wiggy. Let's take it back and see if it's working.
Of quantum mechanics. In the context of this particular theorem, a free choice is defined as a type of choice which is not determined by prior conditions, that is, not determined by the past history of the universe in any inertial frame. Note that this is essentially the same definition we encountered earlier in my previous video when discussing Bell's theorem. So what does Conway and Kochan's free will theorem state? The theorem states that...
Okay, we'll stop there for a second.
Yeah, yeah. So on the last, one of the talks, and then the last or the one before, we got into the delayed choice quantum eraser problem in that experiment, and now how that really forces you to ask the question if in the quantum world there is past and future, if time even makes any sense at all. And if you ask that question, then you wander into the Conway-Kochan free will theorem, which takes that experiment and pushes it to its limit, and essentially says, if we observers in the lab, Alice and Bob in this case, are free to choose what experiment or observation they're going to make on the separate parts of the entangled pair, then the entangled pair must have had free will, the same free choice to decide what it wants to do that the observers did. So their point is, this is not a proof that free will exists, but it says that if we have it, then the quantum world must have it too. The only way of getting out of the corner of giving electrons free will is to admit that in the quantum world, there is no past and future, no here, no there. Everything to them in the quantum world is instantaneous. But then now what do we do with this question of free choice? Maybe we don't have it. So that's the other thing you ponder, is you can't prove that free choice exists. Conway-Kochan doesn't prove even that you have free choice. It just says if we assume that we have it. So free choice in physics, I compare it to the Euclid's fifth postulate, for anyone who remembers their geometry. That's the parallel line postulate. Euclid, in his a list of axioms that you needed to do geometry, stated that parallel lines never cross. Well, if you assume that's true, you get Gibbsian geometry, which is the geometry of general relativity. So we realize that postulate, you can take it as true, you can take it as false. Either way, you get internally consistent mathematics, geometries. But even though they're by themselves, they're mutually contradictory. And sometimes I wonder if in popular thinking, people think that if you prove something is logically correct, that means you've won the argument and that something else now has to be false. But in mathematics and logic, it's possible for two statements to be mutually contradictory, but yet if you take one or the other as true, then you get a completely consistent worldview after that. So you can take, in like manner, you can take the possibility of free choice as a given, and then create a law of physics. Go ahead, do your physics of the universe with that. Or you can reject the notion of free choice, that everything was determined from the Big Bang on, even the choice of observations that Alice and Bob were going to make. Determinism. I think that Laplace's demon, if something comes to mind. Continuous. If you know all of the motions of all the particles in the world, and if you believe that, then how we think and the choices we make, because we're physical objects, have been predetermined from the beginning of the universe as well. You say you're living in the matrix, and that's the catch. If you believe you're living in the matrix, there's no way you can prove that you're not. Or how the saying goes, whether you believe in free will or not, you're right. So, but let's walk it back. Assume that we.
Let me just clarify one thing. You're saying that, like with Euclid's fifth postulate, the parallel lines, the parallel lines postulate. If you assume it's true, you get Euclidean geometry. If you assume it's not true, you get non-Euclidean geometry. They're both complete, coherent, comprehensive systems. And they're contradictory, but that doesn't mean, I'm just clarifying here. that doesn't mean that one of them is true and the other one is false. Or does it mean that one of them is true? Part of what I heard you saying is that you can have a complete, comprehensive, coherent system and it can still be false. Or is it that as long as you have a complete,
No,
comprehensive,
I'm saying you can have two choices and each way ends up with a completely consistent
right?
worldview,
But what is their relationship to
even
true?
though they contradict each other. The question of true and false doesn't make any sense.
Okay. So it's not connected to true, false at all then. I think our connection is so bad today. We're just having a really hard time connecting. There he goes again. And now you're back. So I'm not sure what's happening to our connection. You keep disappearing on me. Are you still there?
Yes, I'm still here. Yeah.
Okay. You disappeared momentarily.
Oh, well, so
It's always like
so
your
did
little,
you, I guess.
your little picture disappears up into the screen and then all of a sudden it comes back down again. It's got to have something to do with
Everything just goes
entropy, I'm
blank for
sure.
you on my side.
What? So
No, I think the machine just echoed.
yeah, so what you're saying is you can have two completely coherent systems and they're both completely consistent within themselves, even though they're contradictory, and that is not connected in any way to true or false. It just is.
Right. You can have two things that are contradictory and both be true at the same time, if you're a mathematician.
Okay. Okay, so
And
that's
but I
something.
know in common usage that doesn't make sense, but in the mathematical world, it's like, well, yeah, of course.
Okay. Well, do you think that that's transferable to the physics world as well?
I believe so.
Okay.
That, though I'm sure people would disagree, but I tend to trust the physics, and I will let physics trump my earthly opinions of things. I'm only a finite, incomplete, individual. My brain doesn't understand everything. So if the physics says it's true, then I'm happy with that.
Okay.
So I want to get back to this notion of free choice. If we take it as true, then we start asking questions. Well, what then? What if? What if the quantum mechanical world doesn't? Locality doesn't bind it there. And choices can be made. Well, how do we make a choice then? This is what I've been puzzling about for a long time. And this would be a great place to show that diagram that she had. I think it was in about 7 minutes that you found.
Oh, from her video?
In the talk.
Yeah. Okay.
Yeah. Yeah. No, at 8:25.
Indeterminism is the idea that there is a branching of possibilities lying ahead of us, rather than just one possible outcome uniquely determined by the past history of the universe. Indeterminism is a necessary condition for our everyday notion of free will to be real. We can still have adequate causality and partial self-determination in a non-deterministic world. Indeterminism simply allows for the existence of alternative futures.
Okay, so one of the reasons I was fascinated by the diagram when I first saw it is when I think about a tree, the way trees work, there's the root of the tree and the crown of the tree. And the root is the mechanism that I don't know what the right word would be, allows the tree to grow, pushes the tree upwards. But the crown is the part that tells the tree how to grow, what the final shape is going to be. And if the crown gets cut off, the tree gets confused about what its final shape will be. So instead of an elm tree ending up looking like an elm tree, the branches just go every which way and they don't make any sense. They don't have a consistent order based on that kind of tree. So you have to have both the root and the crown, which is the bottom up and the top down, are both necessary for a tree. And so I'm wondering if that isn't true also for this branching of possibilities.
Well, in our case, the branch, the lines represent a path through the universe, path through space-time, choices. Each node represents a choice. And as you go forward from now into the future, you pick one line. So at the end, it's not a tree, it's just one line with forks. So this would be a picture of all possible futures. When you look at now, this would be a picture of all possible futures. But as you step forward, you pick only one. So that at the end of the day, by the time you get out to the final end of the branch, there will be just one line. This whole diagram will reduce down to simply one line with crooked points where the nodes were, where choices or decisions were made. So I'll go back to the concept of free choice. To say, free choice in physics or in math, you say something is free simply means it's not bound. It doesn't carry anything more than that. In this case, it means your choices you make for measurement are not bound by the past history of the, not fully constrained.
You know what? I'm going to go back to share screen because
so if you reject the possibility of free choice, it's logically equivalent to saying
I lost you again.
Oh, I'm here.
Okay. So you said you were saying free choice. I put us back on here because I think when you're in the small screen, it's maybe not taking up as much bandwidth or something. I'm so non-technical that I could be completely wrong, but
okay, well,
I'm trying to find a way to get you talking without it breaking up every 5 seconds. So
okay.
So free choice simply means not
getting
bound.
back to not bound by the past, and nothing more than that. And getting back to the possibility that you can have two different choices, whether free choice exists or not, and either way you get a perfectly true universe and laws of physics. So if you reject the free choice, what you're saying is that the past uniquely and unambiguously determines the future. What you're also saying is that the laws of physics, therefore, must be perfectly deterministic. That there is no chance for branching in this case, if you want to, go from this diagram. Which is logically saying that this diagram is simply a straight line from the past to the future with no branches. Now that's kind of a boring universe, but if you reject free choice, that's what you get. And that's one of my problems with the whole notion of predestination. If every line, and it might as well happen instantaneously because there's no branching points. Now, if you accept the possibility that free choice exists, that's the same as saying that the past doesn't uniquely and unambiguously determine the future. That's saying that the laws of physics can't be perfectly deterministic. They must somewhere in there allow for new things to happen. And in this case, you get the branching diagram. Each node in the diagram, again, represents a point when a free choice was exercised. And whatever system it could be, it doesn't have to be a human. It could be, you know, a piece of rock interacting with a cosmic ray. So, and out of that, you pick a branch and you finally get one choice. So the future is determined ultimately by the choices that are made along the way. Now, when I ask these questions, you know, again, Nietzsche's hammer, I look at the theories, I look at what physics has to offer, and I don't see any way that physics can answer these questions. How is the choice made? What happens at the point when a choice happens? This gets me back to the quote from Hume about there's no place where you can put your finger where the choice, the branching actually happens. So if you look at, I compare it to like Zeno's paradox of the arrow in flight, where he proposed if you look at an arrow in flight, at any instant, it's stationary, it's not moving. So how does it move? And my question is, if you look at a path through space-time, as where does the choice happen? At any point you look at it, they'll either be on one path or it will be on one of multiple paths. And the question is, how does that branch happen? What is going on in the universe that lets a choice be made to go from one possibility to multiple? Now, I'm out in the tall weeds now, but I think this is a pretty valid physics question, which is not being answered. So each time the branch is made, each time a choice is made, you only know what you know locally. So whatever is pushing complexity, you know, if the universe is doing this branching thing like we see in the diagram, and it's trying to tend itself towards more complex rather than more random, there must be something biasing the choices as they're made that makes the universe want to go towards a more complex structure rather than a more random structure. So if you look at entropy as a process rather than an end point, then disorder is really the process of forgetfulness. Each node, each choice that is made forgets information. Information is lost about where you were, where you started from, until you reach a place where all information of where you started from is lost. And that is what we refer to as the greatest disorder. And then we try and measure that as, you know, mathematically, and that's where entropy has come to stand now. But like I say, for me, it's the process that fascinates me, and simply doing the static into the line definition of entropy as disorder doesn't answer the question how you got there. So I'll take a breather and let you ask questions back.
Well, I was struck by Cesar Hidalgo in his book when he was talking about, well, first of all, he talked about steady states and disequilibrium, and then he talked about static steady states and dynamic steady states, and differentiated those, which I thought was very helpful. But he was talking about a particular kind of steady state that is like when water is in a bathtub and you let the water out of the bathtub, the water will form that little whirlpool. And that whirlpool is a kind of organization, let's put it. It's a creating of order, but it's in a, I think he called that a dynamical steady state. And then he went on to say something about, and I'm not linking it up all in order because I'm not looking at my notes, but he was talking about how after chaos comes the information. So the growth of information comes after chaos, which is certainly the way we see it at the human level in our lives. You go through a period of chaos and you've learned something from that, and hopefully you've learned something from it, and you go on stronger and wiser after the chaos. But that also apparently is a physical principle, that after the chaos comes the information. So wouldn't that be one of the ways that complexity grows, by the input of chaos into the system?
Well, that's one of the popular approaches to it. Complexity theory, I think, is the category it gets lumped into.
Mm-hmm.
And the word that comes up right now is self-organized criticality.
Mm-hmm.
When you push a system into a very strong non-equilibrium state, you'll see order spontaneously appear. It could be eddies of current in a river, convection currents in boiling water, the bathtub drain thing. In fact, our weather is a perfect example of that. You have heat coming in from the sun, temperature gradients from the equator to the North Pole. You've created a very unstable non-equilibrium situation. And so the air, the atmosphere is trying to remedy that, and it organizes into hurricanes and tornadoes and storm fronts. And so that is one thing, but it doesn't answer the question in the end, how complexity grows. If we look at things that we consider complex, again, keep asking questions, don't just stop. The things that catch our attention are the things involving intelligence. Somehow or another, we see intelligence, either manifested in the item, or a result or a product or artifact of some intelligent system. Something is making decisions and things move forward. So that is what I think intrigues us the most, that level of complexity. And self-organized criticality, that kind of organization, that kind of structure you see form spontaneously, is not capable of computation. It's not capable of making choices. So that's where I keep coming back to, how do you make a choice? And what actually happens when you make a choice? There has to be some kind of input, a decision process, and then an action back. And I think a lot of people have discussed this in a lot of different ways. There's a loop going on in there. And David Deutsch in his constructor theory gets there. He hints at that. He's understanding that there's some kind of a loop going on that makes things happen. So
Well,
constructor theory.
He's asking, one of the reasons I thought there was a connection between constructor theory and emergence was that he's asking the questions in a way that looks at the system as a whole, basically looking at within this system, what is permissible and what is not permissible. And you had pointed me to a video of Philip Clayton's where he talks about emergence. And he was explaining that there are certain systems, like, let's say, chemistry, where once we understood what was happening, we could construct the chemical table of elements, and we could then see what the system was and predict where the missing elements would show up, and what their components would be based on what was already there. But before that was evident to us, there would have been no way that we could have constructed a chemical table of elements. We had to be able to see the chemicals and see their properties in order to set up the system for ourselves. So he's talking about that as a way of looking at systems as they currently exist and seeing what the principles are that govern the system. So I thought he was calling that a kind of a weak emergence. And so I thought that was similar to what David Deutsch is doing with constructor theory, looking at the system as it already exists and then asking within this system what's permissible and what is not permissible.
Well, the first thing on the chemical table, I would consider that strong emergence. because
Okay.
somebody's noticed patterns, and then you start organizing these elements that you know according to the patterns of how they react chemically, and you start to see a structure, and then you realize there's places missing. So what you've noticed is a pattern, and that pattern is now instructing you to look for more things. So to me, that's a top-down causality. There's a pattern out there that you're sensing, and you're reacting to it, and now you're trying to fill in the pieces. So the pattern exists without you, and it's telling you what to do.
Would you say
Kind of like a
mathematics is
muse.
kind of, would you say mathematics is kind of the same thing?
Yeah, exactly.
Okay, okay.
So-
Then I'm on the right track.
Yeah. It's the old question, is math discovered or invented?
Mm-hmm.
If it's discovered, then we're sensing it. We're pioneers. We're the scouts that went out into the frontier and said, well, there's, the terrain is this way, so there must be a lake over there. And then you gradually map the frontier that way by asking questions, noticing patterns, and then walking over and looking at it and say, yep, sure enough, there's a lake there. So the patterns exist before us, and somehow they instruct us or pull us. And there again, I think anomaly and curiosity. That's how the patterns reach out to us and pull us forward. I've noticed a lot of people don't have curiosity in life. So that's a blessing for people who have it.
Well, but there's also another element of these systems like chemistry and mathematics is that the system has its own constraints. It has its own limitations. You have to abide by the constraints or the limitations of the system in order to make progress in understanding the system and in seeing the way it's laid out. And so those constraints, so when Philip Clayton was talking about the difference between weak emergence and strong emergence, he was saying that weak emergence is basically where the constraints of the system determine how did he put it? The constraints of the system determine the behavior of the system, I think is the way he put it. And he was saying that you can't, he didn't think that that was adequate to explain the kind of emergence of human thought or the kind of emergence of an animal within its ecosystem, an organism within its ecosystem, because it's not that they are only constrained by their physicality to behave in a certain way, because they're confronted all the time by ways in which they must interact with the environment. And so in that interacting with the environment, they have to make choices. Basically, they have no choice but to make choices. Let's put it that way.
Yeah, well, that's the nature of life. Yeah, one of the distinctions between strong and weak emergence I've noticed is that you're always dealing with a bound system. Emergence means the many become one. Somehow everything comes together, a collection, a collective. Something happens and now it starts behaving as a single unit in itself. And it has its own rules. So the complexity now of how the system works internally is lost. You don't have to look at it. It becomes simple now from the outside. The distinction on weak emergence, the boundary is imposed from the outside. So thermodynamics is a classic case of weak emergence. You have a box, a piston, a cylinder. There's always a boundary that is built by something which constrains the system. And once the system is constrained, the weak emergence happens. Strong emergence is when the system makes its own boundary. It's bound together internally by something, social order. So a flock of birds would be an example of strong emergence. It's held together by something going on inside, not by anything outside putting a wall around it. So when you see strong emergence, you see a cooperative effort going on. That implies more than just weak emergence, which is just the collective behaviors of the laws of physics all of a sudden create group behaviors which look simple now. Again, so like the eddies in the stream, the self-organized criticality phenomena that people look to that come out of complex systems or non-equilibrium systems, they only last as long as the boundary conditions that have caused it are still there. An eddy won't flow off in the creek and just stay there forever. It will last only as long as the initial start and then the momentum of the current as it stays together. But as soon as you break it up, put a stick in there or something, it's gone. So that is something you need to look for. Distinction not always brought up in these discussions. But if something is sticking together, strong emergence, self-organized, it has an immune system. You can disrupt it and it will heal. It will come back together. It seems to have a will of its own. I guess I'm wandering off now, so I better stop.
Well, I found it tremendously helpful, so it's okay with me if you wander. Okay, so I'm sorry I got you waylaid there. Back somewhere where you were talking about when we see intelligence, self-organized criticality is not capable of computation. So you were talking about the idea that you have to figure out how complexity happens. You know, you were talking about Zeno's paradox and the arrow that is stationary at any given moment in time, and yet somehow it's moving through, seems to be moving through space.
Yeah.
So at what point does choice happen? Does a particle go here and not there? Now, from the point of view of quantum physics, if I understand correctly, that happens at the point of observation, right? At the quantum level?
The observer is just a classic. What constitutes an observer or measurement is one of those wide open questions. Yeah, I think you're more onto the right track when you notice a photon detector, electronic detector, anytime a classic system interacts with the quantum world, that constitutes a measurement or an observation. So it doesn't have to be us.
Oh, right. Yeah, I
completely
understand. I mean,
non-intelligent.
but it has to be some intelligent, some system that has.
No, it doesn't. No. Well, I guess what I'm trying to get at is intelligence requires free choice in order for it to happen. But free choice by itself is not intelligence.
Oh, no, I didn't mean that
there's
free
multiple
choice was
pathways into
intelligence,
the future.
but what I said was, I was talking about the detector, whatever the detector is, whether it's a classical detector or if it's a photon detector or whatever, that has to have been built by an intelligent.
Yep.
Okay, that's what I was getting at.
Yeah.
I wasn't saying.
Yeah,
that
yeah,
free
you
choice-
can. That's why some of these experiments really open up, because you start out simple. Well, there's Alice and Bob and they're sitting in their labs, and then you go, well, how do you know Alice and Bob weren't predetermined? And well, what about the detector? You know, it was made by somebody, and who knows? And it wanders off, and so you end up back to the place. Either everything that happens to us was determined at the Big Bang, or it wasn't. That's the hard question, and it demands an either yes or no answer. You can't fudge it. So pick one or the other. And if if we live in the matrix, then we're done. If we don't live in the matrix, then choice matters, and we have a whole world we can explore of possibilities. So just trying to recap to complete the thread was that life happens because complexity happens. Complexity happens because it's possible for free choice. that from the past, from going from the past to the future, one can make decisions, or something can make decisions, which leads to away from randomness and towards organization. And that gets us back to quantum eraser and delayed choice, and then back further to Jordan Peterson and Krauss. Anyway, that's how my brain works.
So life happens because complexity happens, and complexity happens because of free choice. And free choice, and it happens because you're moving away from randomness and towards order, I think is what you said.
You can, yeah. Choice doesn't mean that you go to order. I mean, you can
Right.
choose to go to completely randomness.
Yes,
You know,
you can choose either.
It's a necessary but not sufficient condition, as they would say. So it's one of the tools that intelligence requires to be there in our universe before it can exist and function.
Well, one of the things I was doing in preparing for this was going back over the notes of our previous conversations, and we had spent quite a bit of time talking about the lock and the key.
Mhm.
And I thought that was a pretty interesting way of looking at the moment at which choice is made. Now,
Mhm.
there's so many things wrapped up in that. I mean, as we determined
I
after we
know.
talked about it quite a bit, that the lock and the key, the lock presupposes an intelligent designer because
Mhm.
it is capable of sensing whether or not the key is the right profile to fit the model, so that it knows whether to open or not open when the correct profile is inserted in the lock. So that's already presupposing some kind of an intelligence. But when we were talking about the possibility of non-biological life, we were talking about, is there anything in the non-biological, strictly chemical macro world that would function as a lock and a key? And I don't know if we ever even answered that question, but when we were discussing that, you were talking about computation being basically the yes, no questions, right? And then
Mhm.
information being the answer.
Yeah, this works. I think that's a useful way to approach it.
But in between there, the if else then logic is the I guess the part I'm having a hard time with is I think of the if else then being also the computation, but I think you're separating those two things, right?
No, I don't think so. Anytime there's a conditional if else then process, that's a computation.
That's a computation. Okay.
Yeah,
Okay, that clears it up
right,
for me
yeah.
then. So if they're the same
We tend
thing,
to, I think people, yeah. So something selected of the possible futures. In this case, it's the lock and key, the profile decision-making process. The computation, the program, so to speak, was built into the construction of the lock mechanism itself. There is no program, there is no system running it. And I think that's what people need to grok sometimes.
well, I mean, as I understand, I had a conversation last year with a neuroscientist who works on fragrance, but before that he had worked on vision. And the way he described it, the neurons have that lock and key kind of a system.
Yes.
The way neurons sense is totally this lock and key mechanism.
Exactly.
Yeah. So did you ever think of a place in non-life where this lock and key shows up?
Well, not yet. Uh,
But I
Yeah.
wonder if this part of this self-organized criticality isn't somewhat like that.
I don't think so. My inclination is to look for the simplest example. When people go into complexity theory, they're wandering into the world where the most complex stuff happens.
Okay.
And my intuition, my experience, I guess for what it's worth, is that if you want to understand something, you go look for the simplest example, cleanest example you can find of it. And I think the lock and key is the simplest example I can think of a computation, where you have an input, a decision process, and then a responding action back on the world. And so if you can't, so that's where I begin.
Well, okay, so then let me just explore this a little bit more with you. We had talked somewhat about, well, one of the things that Cesar Hidalgo talks about, and you had also mentioned it in an earlier video that we did, is that when you have the gas in a box and then you make the box larger, or you move the little wall over so that the box gets larger, the gas molecules are still moving around. So it's still a dynamical steady state in there once it becomes a dynamical steady state once there are as many particles or molecules moving left to right as there are moving right to left, but they're still moving. It's all moving around in there. But there's been an increase in entropy when you increase the boundary, but there has not been an increase in disorder. Is that correct? I think that's what Cesar Hidalgo said.
Yeah, I can't remember exactly. But
well,
the example
I guess it's kind of
gave,
irrelevant for the question that I had was, so, but if you make the boundary smaller and make it smaller, all those molecules get packed into a space. And if you make it small enough, then something's going to happen with those gas molecules.
Yeah.
Right? You're putting some kind of pressure on them by restricting their boundary.
Right. In real life, there'll be a phase transition at some place. They'll turn into a solid, a crystal lattice, or
would that be a decrease in entropy?
Yes. Mm-hmm.
So
yeah.
So is it a universal that when you expand the boundary, entropy increases, and when you restrict the boundary, entropy decreases?
Only if you do it reversibly. If you increase the boundary irreversibly, then the entropy doesn't change. That's the conundrum. Again, ask questions until you find that place that the traditional textbook thinking can't answer. So
when you say, if you increase the boundary irreversibly, would that mean essentially just removing the boundary?
If you have the boundary and then all of a sudden you just move it out real fast, faster than the molecules bouncing around can catch up with it. And then you stop. And then the molecules keep bouncing around until they finally fill up the cylinder again, and they're hitting the far end. And now there's a new state. And you might want to, well, is that more disordered because it's the same molecules, but it's a bigger area? But since no heat was transferred, the entropy has not changed. So that's one of the points where I go, well, then entropy is not a hard measure of disorder, because I've just disordered the system, but I haven't changed its entropy. So there must be something else going on here. And that's when I look at the process and I look closer. Okay, what's going on individually with each of the molecules rather than looking at them collectively? Just look at each one alone by itself. What is it doing? What's it responding to? And then I notice the walls of the chamber are part of the system. Every time the molecule hits the wall of the container, it bounces back. The walls randomize the motion. So the drawing, the branching drawing we have, if it was one of the molecules bouncing around, its direction gets changed when it hits the wall. And now the wall kicks back on the molecule, it goes a different direction. But the wall of the chamber are molecules or atoms moving around, they're jiggling at a temperature. So their jiggling randomizes the kickback on the molecule that's in the gas. But then the wall of the chamber is interacting with the outside world. And so when I take my attention off just entropy being disorder, a measure of the final state, and I look at all the processes that go on as the system reaches equilibrium, then my attention gets drawn to the boundary, the construction of the container. What is the container? Is a heat bath. And then I realize that everything is tied to the rest of the universe. That's playing a role in it as well.
Yeah.
And then at which point my brain kicks out of gear because it just gets overwhelmed.
Well, see, my brain is very small and very simple. So I just stay on one little thing. So my brain is still thinking about when the boundary gets restricted, gets compressed, and is there a point at which, this is a really stupid question, but is there a point at which those molecules have to make a choice? I mean, when Dr. Sharon Glotzer did her research on particles and how they act when you remove space, they seem to have a desire to organize in a way that permits them the maximum amount of space given, to find a configuration that gives each particle the maximum amount of space. That seems like a lock and key thing going on, some kind of a choice. I mean, is it a rule of the universe that every particle is it a rule of the universe that every particle wants maximum space?
I don't know. Before a particle can make that decision, it has to know what the rest of the universe is doing. So, and it doesn't. Particles only know what's in the immediate, what their immediate neighbors are doing. So that's why I step back from a lot of the standard views of entropy, because if I look at the actual process that is happening, the individual shapes in her simulations, I believe her work was done with computer simulations, they don't know anything except for what's their nearest neighbor. And they're bouncing off their nearest neighbors, and their nearest neighbors are bouncing off them. And so you end up with this random motion, random walk through the possibilities that tends to maximize the possibilities. I'm out of gas here because this requires this requires some math, and I'm not ready to do that now.
I'm sorry, my pea brain asks these questions that
I know. That's why I keep going. I keep trying. Someday I'll say something and you'll go, okay, I've got it.
Well, I think that I understand a lot of what you're saying. It's just, it opens up new questions in my mind and I can't seem to shut off the flow.
Well, I know, but then you're where I'm at now. And I'm reluctant to ask those questions because they often lead into possibilities that are not standard. And the one that's really intriguing me right now is that the actual structure of space-time is discrete and finite rather than continuous. And if you make that assumption, then you get a whole bunch of stuff for free. The arrow of time automatically gets a direction. the notion of free choice becomes possible. Quantum world goes off in its own direction. But that's kind of a renegade thing to say. But I explore it. So
Well,
that's part of
but
the.
why is that a renegade thing to say? When, I mean, I thought one of the big breakthroughs of the 19th century was that was this idea that photons are discrete and finite and not continuous.
But all the mathematics that we use surrounding them is differentiable and continuous.
Well, so you had mentioned that in your email, and I was wondering why, if we know that light is not continuous, then why do you use mathematics that's differentiable and continuous to describe it? Is that because that's all you have?
That's all they have. Yeah, that's all. We started into quantum mechanics. We started from the classical world. Classical mechanics is universally calculus, continuous and differentiable functions. As soon as you impose continuity on everything, all the laws of physics automatically become reversible. That's, that was a solution to Zeno's paradox, the arrow in flight, was Newton's calculus. All of a sudden now, with infinitesimals, we could deal with stuff like that. We didn't ask what happens at the instant. We asked what happens in a limit. It gave us the tools to avoid asking the question. And ever since then, calculus has been the go-to mathematics in all of physics. But as soon as you embrace calculus, you've embraced the continuum and you've embraced reversibility. So something has to break that. And if the universe is finite and discrete, then you automatically get that. Because every step now it brings a round-off error, so to speak, with it. And so that will automatically introduce a drift. So, but that's kind of a weird place. It gets rid of string theory, that's for sure. It deals with the question of why you can't meld quantum and mechanics with relativity.
So you think that instead of trying to, let me just guess what you're saying, that instead of trying to meld the quantum world with the classical, or quantum world with the classical notion of gravity, that what you really need is a new mathematics for the quantum realm.
Yeah, approach it, mathematically. Let's start over again with the assumption that the universe actually is finite and discrete.
Have you tried
that? But the quantum world doesn't. I don't know. I haven't encountered it. But like I say, I quietly keep these ideas to myself, and you pry them out of me. And so
but you're a mathematician. I mean, couldn't you mess around with that?
I was trained in both.
Yeah.
Yeah, I'm too tired. I don't have the brain I had when I was 25. I'm sorry.
Well, we need to find a 25-year-old mathematics guy to give that a try.
Yeah, but he has to be really crazy too. That's a double qualification that's hard to find.
Well, I'll bet somewhere on my channel there is one. So we went a long way around the whirligig, and I'm not sure we accomplished what we were going to, when we promised we were going to accomplish. But it certainly has.
In a funny way, I feel that I have. I think we've touched all the bases now. I think the roadmap is out there. And if someone is patient and tries to walk through it, I think there's enough there to make sense out of.
Well, I really like the quote that you took from Nietzsche, and the illustration of the bell, and how important it is to keep asking questions until you find the place where there's no answer.
Yes. And don't be afraid to do it. And you're wrong. So what? It's fun. You ask a question, you say, okay, well, what if? And then you make the effort. the responsibility is now on your shoulders to answer the question and to explore. And so that's a good chunk of my life has just been playing the what if game. And then, well, if this is true, then what does it imply for that? And then you just keep going until you find another contradiction. And then that, you know, ping pong ball, and, you know, you're just going off and go off in another direction yet. And that's the fun. And that's the reason why I stay away from the theory, TOE's, theory of everythings, that people are trying to push, because generally they don't offer you the space to ask questions. You know, once you have a theory of everything and it explains everything, then there's no room to ask questions anymore. So then what's the fun?
Well, yeah, I mean, I can understand that, although I get fascinated by the theories of everything, but that's probably because I have a small brain. But one of the things that makes me think about, well, it's not exactly a theory of everything, but, you know, we're still looking at this picture here of this tree of possibilities. If I think of this as a, instead of a tree of choices of possibilities, but just look at it as the shape that it is, right? The beginning of the universe starts out very, very small, and then it expands, and it expands more as time goes by. So time is moving along seemingly on some kind of an axis, and around time, space grows. And at the same time that space is expanding, entropy is increasing. Not necessarily any connection between the two, but it's happening at the same time. And it looks to me like a root and a crown. This is where we're going. And the crown is what informs everything, what shape it should be trending towards. But when you look at a tree, not every elm tree is identical, but they're recognizable. So the crown has told the elm tree how to grow so that it looks, so that it inhabits the world of an elm tree. But it still has many, many choices about where each leaf might go and how long each branch might be and where the branching is going to take place and all of that. So there's a lot of freedom within the elm tree, but it still is the root and the crown working together so that the elm tree becomes what it's supposed to be. And I kind of wonder if there's not something like that going on in the universe as a whole. That there's a crown that's telling, giving some sort of input that's guiding, giving some guidance. The video you pointed me to with Philip Clayton, the way he describes strong emergence is that he says it looks to him as though the universe is upwardly open. Which is something that the strict determinists don't want to acknowledge, right?
Right. Well, here, I think I have a much better way to look at this diagram.
Okay.
That might be open up some more windows. This is just a picture of one person. Imagine this is just one person's life, and each branch is a yes or no decision. But you're not alone in this universe. There's a lot of other people. Each person has their own decision tree of possibilities ahead of them.
Right.
As you make your choices, you're not a branch in a tree, you're a thread. You are one line threading up, and somebody else is making choices, and their one line becomes a thread. And so all of us out there are making decisions that have trees, that's the pattern, but we pick one line out of that tree and we become threads that if we make our decisions right, we weave into a tapestry.
Yeah.
The threads intertwine and become something bigger than any of us individually, and potentially could tell a story. when it's all done, of the choices we made. So what we star as a tree could actually become a tapestry if you combine a whole bunch of people making their decisions and weaving their choice trees together. I don't know. That seems kind of nice way to look at it.
Yeah, I like that. That's a good place to tie it up, maybe.
Mhm.
As always, Glenn, I always feel so privileged to have the opportunity to talk to you and hear your thinking, and appreciate so much you're giving us the time. And I hope that if the internet connection issues are on my side, I'll try to get them worked out before we talk again. So I apologize to the listeners who made it this far.
Yeah, well, my wife, Paula, she has problems doing her teaching, so this is not unusual for us. So I
Okay,
guess it's just our connection here.
yeah, okay. Well, it sounds good. I hope you have a great weekend, Glenn.
Same to you.
Yeah.
Thanks again.
Yeah, okay. We'll
Right,
talk to
take
you
care.
soon. Bye-bye.
Bye.